Chapter 12, and so Squircle. We're going to continue with the discussion around Squircle scales in two sections. I'll introduce a concept that I call the balanced Squircle scale, and following that path in section B, we'll find a formula for certain sums of arc that reveals something about these balanced scales. So to start, let's look back at Squircle scales from the end of chapter 11. This visualization shows each pitch as equidistant from each other, like keys on a piano. But we know that generally, each pitch is a different amount of tones away from the next. Using an axis of pitch instead of note name, the scales look like this, which in my opinion is a very satisfying visual. If you track the colors, you can see how the Squircle scales develop in a very continuous way. The absolute pitch of each node goes up and up until it eventually comes back around to the beginning. We could also visualize these offsets in two dimensions, where the horizontal axis is note name and the vertical axis is pitch. I'd call this diagram the scale steps. This makes it easy to see how large the difference is between any pitch in any Squircle scale and the pitch that shares the same note name in 12-tone equal temperament. This is where I got the idea of a balanced Squircle scale. First, though, we should define a function called scale, which is the ith element of delta p mod 12 sorted from least to greatest. This gives us an intuitive way to call any pitch, in semitones and cents, from a given pitch class. For example, with p equals 4, we have scale base p of 6 is about 6.446, since G flat is the 6th pitch class, and here it is 44.6 cents sharp of 12 tet G flat, giving it a value of 6.446 semitones. Scale of 8 is about 7.537 because A flat is the 8th pitch class and the 4th degree A flat is 46.3 cents flat. We can define the offset delta of the Squircle scale with 12 tet by just taking the difference of the two, the latter of which is just the identity function, something that would be easy to show by yourself if you wanted to. A balanced Squircle scale is a scale such that the sum of all the offsets cancel each other out, leaving the overall scale no sharper nor flatter than 12 tet. To zero in even more, a balanced p is any value of p that satisfies the same criterion. Now let's take a look at that criterion. Expanding the summation using delta's definition, we can show that a balanced scale is a scale such that the sum of all of its semitones is exactly 66. Going deeper through the definitions and using the commutativity of addition, we eventually see this sum, which for balanced p is always a natural number. Now this sum is something I really want to talk about in this video so that you can get a fuller perspective on it. More specifically, a sum of this form, where a, k, and b are non-negative integers. We're going to come up with a general formula for this expression, and in order to do that, we have to first find a formula for this one. If you don't want to sit through the derivation of this formula and instead skip to how this relates to balanced Squircle scales, skip ahead until the green at the bottom of the screen goes away. We're going to start by expanding the sum and grouping it by multiples of a. So we'll have the 0th term plus 1, 2, 3, etc. until we get to a minus 1. Then we have a plus 1, a plus 2, all the way until we get to a plus a minus 1. That pattern will continue until we reach the k minus 1th iteration, which ends at k minus 1a plus a minus 1, which is the sum's ak minus 1th and final term. This grouping makes it easy to see the way that we can rewrite the sum like this. Now we can distribute inside arc and use the complementary angle identity to separate it into two double sums. Now we want to expand both sums and notice that we can group these in a way that satisfies the complementary angle identity. The 0th term is 0, so we can knock that out, but the first term plus the last term is arc of pi over 2. The second term with the second to last term is 2, and so on. Because we're putting things in pairs, we'll actually have different paths if a is even or odd. So let's start with even. We'll go as we did with the first and last, second and second to last, and keep adding until we get to the one right before and after a over 2. Then finally, the a over 2th term. So using the complementary angle identity, we now have a over 2 minus 1 arc pi over 2's plus the final term, which simplifies to arc of pi over 4. We'll factor and simplify this and get a form for which we'll do one final step, multiplying by a over a. This turns this expression into a form that is actually the sum of non-negative integers up until ka minus 1. That means that these two expressions are equal when a is an even number. For odd a, we'll do a similar process, which I'll just show on screen. This leads us to the same answer, which means that this equation is true for all values of a and k. I call this the decomposition formula, since it looks like the terms of the argument are getting separated. The n stays within the sum, and the 1 over a leaves arc. For the sake of completeness, I will now go over the form for these arc sums going to any number of the form ka plus b. Our first step is to separate this into two sums, one of which we can use the decomposition formula on, and for the other, we can rewrite the bounds to something simpler. Now we can use some arc properties to split these terms up. We can solve the middle sum and then factor out a 1 over a arc pi over 2. Finally, we can rewrite that term under the left summation. This is the formula for all the arc sums going to any positive integer. Seeing as we have two formulas, I'm going to call the top one strong decomposition and the bottom one the weak decomposition formula. I think that they're both worthwhile formulas in and of themselves, which is why I want to make note of both of them and not just one. Side note, this statement is also true, which may be easier for you to memorize. But the reason why I mentioned this formula in this video is so we can get back to this. Recall that a balanced p is a value of p such that the sum of all the differences between that pth degree Squircle scale and 12 tet is 0. Via the definitions, it follows that this sum must be a natural number. Using the decomposition formula, we can rewrite the right-hand expression, which reveals that arc of pi over 2, and therefore the circumference of the Squircle, is a rational multiple of pi. I'll say it again. If you have a balanced Squircle scale, its Squircle has a circumference that is a rational multiple of pi. And through some computation, I found a pattern with these circumferences. So I pose that all balanced p Squircles have a circumference of the form 2 pi times 2k plus 1 over 77, where k is a non-negative integer. And it's also about time that I reveal some balanced p values. Of course, we have p equals 2, since all the deltas equal 0, but there is also approximately 1.3023, 1.5233, 1.7489, 2.6441, 3.0822, 7.2240, and 51.7272. These values are in order from least to greatest, not skipping any at all, and you can see that each subsequent balanced p is further from the last. Since the limit as p approaches infinity of Squircles exist, I pose that there are a finite amount of balanced p-values greater than 1. Oh boy, that's it. Balanced p. Let me know what you think. And let me just tell you right now, this idea of balanced scales is based on nothing but vibes. I have a feeling that musically, maybe something about these scales is special, but if I want to start making music with Squircle scales, I gotta find my footing somehow. Look out for a music video for a song using a Squircle scale. Bye!